Lesson 3-4, torque. Statics is the study of forces in equilibrium. Equilibrium means there's no acceleration. We've already learned the first condition of equilibrium is that the net force has to equal 0, because F equals ma, which means our net force in the x is 0 and our net force in the y is 0. However, things can still rotate, so let's think of opening a door. Which opens the door the best? And picture A. Why? Because you're pushing on the very outside of the door and you're pushing it open. Figure B, you're pushing by the hinge. That doesn't work so well. And figure C, you're pushing along the length of the door. That's not going to open it. To open it, you need to push that way. So picture A works best. A big force means there's a large torque. A force away from the pivot point produces a large torque. And a force directed perpendicular to the door also produces a large torque. So we need force away from the pivot and perpendicular. So torque is R cross F. That's the cross product. So it's vector R cross product with vector F. This means we use the component of the force that is perpendicular to the lever arm. So it'd be R times the perpendicular force. Or R, the magnitude of the distance, the radius, times the magnitude of the force, times sine of the angle between the force and the radius. So this is our angle theta. There's your force, and there's your radius. Just like everything else, so counterclockwise is positive, clockwise is negative, and its unit is a Newton meter, because it's the radius, the meter, times the force, which is the Newton. Let's say you're meeting the parents of your new special friend for the first time. After being at the house for a couple of hours, you walk out to discover the little brother has let all the air out of one of your tires. Not knowing the reason for the flat tire, you decide to change it. You have a 50 centimeter long lug wrench attached to a lug nut as shown. If 900 Newton meters of torque is needed, how much force is required? Well, the distance, our radius, is 50 centimeters. Which is 0.50 meters. And our angle is 120 degrees from the picture. And our torque, it says, is 900 Newton meters. So torque is R F sine theta. R is 50 centimeters or 0.5 meters. F is what we're looking for. And our angle is 120. 0.5 times sine of 120 is 0.4330. So divide, and our force comes out to be about 2,078 or 2,080 newtons. How could we make that force less? We could probably make that force less by making our angle 90 degrees, so it's perpendicular instead of 120. So the first condition of equilibrium was that the net force has to equal 0. Our second condition of equilibrium then is the net torque has to also equal 0. That gives you equilibrium. A 5-meter long, 10-kilogram seesaw is balanced by a little girl, who's 25 kilograms, and her father, who's 80 kilograms, at opposite ends as shown below. How far from the seesaw center of mass must the fulcrum be placed? Well, to do this, we would probably have to add up torque. So we're going to say our net torque equals 0. So what torques do we have? Well, we have the weight of the girl and her distance. And we've got the weight of the father and her distance. So the center of this board is at the 2.5 meters. So they're each, the girl and the father, are each 2.5 meters from the center. So if I do the weight of the girl times her distance plus the distance of the father times the weight of the father. But we also have the board, so we have the distance of the board and the weight of the board. Should all equal 0. Well, the girl is 2.5 meters plus x from the fulcrum, and her weight is 10 kilograms times 9.8 meters per second squared. The board is, the girl is 25 kilograms. The board is x distance away, and it is 10 kilograms times the 9.8 meters per second squared. Now, the angles are all 90 degrees. They're all perpendicular. Sine of 90 is 1, so I'm going to ignore the sines of 90s because they're just 1. The father, though, so both of those are rotating the board counterclockwise. The father, though, is rotating the board clockwise, so the father's negative because he wants to rotate it the other direction. And he is 2.5 meters from the center minus the x. So it's 2.5 minus that x to give his distance from the fulcrum. His weight is 80 kilograms times 9.8 meters per second squared. All right, so if I distribute 25 times 9.8 is 245. So I have 612.5 newtons plus 245, that was Newton meters, newtons times x. 10 times 9.8 is 98. So I have 98 newtons times x for the board. And then the father, 80 times 9.8. So the father's weight is 784 times the 2.5. It's 1960 Newton meters minus 784 newtons times x. All right, if I collect like terms, the newtons with the x's, now remember the second one is minus. If I combine those, I get 1127 newtons times x. And if I combine the Newton meters, that'd be 612.5 minus 1960. I get negative 1347.5 equals 0. Move that to the other side. Divide by the 1127. And I end up with approximately 1.20 meters. Technically, it's 1.195652174, so it rounds to 1.20. Now, how much force must that fulcrum support? So that's going to be the sum of the forces. So this is talking about the net force has to equal 0 because we're in equilibrium. So we have the weight of the girl going down, the weight of the board going down, the weight of the father going down, and then we have, so I guess those should all be negatives, and then we have the fulcrum pushing it up. So upwards would be the force of the fulcrum. Well, the girl's weight we found before was 245 newtons. The board's weight we found was 98 newtons. The father's weight we found was 784 newtons. And we're looking for the force of the fulcrum. So I get 1127 newtons. Add that to the other side. The force of the fulcrum would be 1,127 or 1,130 newtons if I use three significant figures.